Hi, and welcome to CS109. Today it's going to be about machine learning, so it's me up front here. But before we start, I'm going to have to do a few announcements for you. One is I got an email about this Harvard X Interactive Learning Challenge, and it looked fun, so I thought you might want to know about it. So it's a challenge about creating an interactive visualization for the binomial distribution. So it's for teaching purposes. So if you want to get your hands wet with a bit more interactive visualization stuff, unfortunately, up to now, I don't know of any good Python libraries that allow for interactive visualization. I think there was one that does not, it's still a bit buggy. It's not, people told me it's not sufficiently developed yet to use in a class setting. But if you know about resources, want to give it a try, this might be a fun idea. The deadline is fairly soon, though, I think. November 1st. So it's basically the rest of October that you have if you want to compete in that challenge. So the link is in the slides, in the notebook. Also, the notebook, as always, is on GitHub. Actually, last time it wasn't on GitHub because I thought nobody was using it, but then I got a few requests. So this time the notebook is on GitHub if you just want to do a quick poll. And it's also linked on the CS109 homepage. I don't have many interactive things, though, today. So if you don't download it, you'll be fine following everything along. Then homework. Homework 2 solutions out. We had to wait a bit with that because we had a latecomer, but they're posted now on the webpage. And homework 3 is basically ready. We're waiting for a final go, and they will be posted. Most probably after the lecture, I think latest by tonight. What? Sorry? Homework due? I think it's always, right? The next week, Thursday. Oh, and one comment, just because there seemed to be confusion about this. In principle, we do not allow you to use 3 late days per assignment. It's 2 late days, because I got emails, where's the homework 3 late day box? There is none, right? You should use only 2 late days per assignment. Even if you have 6 in total, right? But per assignment, in principle, there are only 2 that you can use. So you need to hand in latest by Saturday night, right? Yeah. OK, now that we got that cleared out, introduction to machine learning. So what's it all about? It's all about analyzing training data. And roughly, all of machine learning, people like to categorize in these 2 big groups. And that is supervised learning and unsupervised learning. So supervised learning is all about making predictions for new data points. You get data from somebody, and this data is labeled, right? So it's a couple of faces, and it's the name of the person who is in the picture, for example. And then you need to train a classifier, and the goal is for future pictures to predict who is shown in that picture. Right? So supervised because there is somebody giving you information about the labels. You can think about it as having a teacher. And then there is unsupervised learning. In unsupervised learning, this happens a lot, I think, in biology. I had a couple of biologists who were like, I have this great new technique that can get me terabytes of data overnight. Here, can you find something? Right? This is unsupervised learning. You don't have much information about what is in there, and your task is basically to find interesting structures, patterns in there. So we have a few examples for supervised learning. As I already said, face detection is one, right? Also, I think some image processing softwares by now allow you to do face detection initially on your photos, right? And what you normally have to do is you have to provide labels in the beginning. You have to show them at the beginning, this is Uncle Sam. And then it tries to find all Uncle Sam pictures in the set. Handwritten digit recognition is an older problem. I think it's solved. Like face detection, No, not, yeah, it's on the verge. It's actually getting pretty good. But the handwritten digit recognition is much, much better. And there is a data set that we're also going to use in class today that has been around since the 80s. And you can see like the error rate going down, 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 down. And then sound classification for hearing aids. I had a few colleagues doing my PhD who were working on this. It's actually when you have a hearing aid, settings where there's a lot of noise around you can be quite disturbing because the hearing aid is just emphasizing everything around you. So what you want is you want to classify something that you're hearing and then maybe say, this is a construction site. Please tune the volume down. This is really nice classical music. Please tune the volume up. So you want the hearing aid to be intelligent in the way that it reacts to the different sounds around you. And there you have the user then with the input device saying, this is music, this is noise, I don't want to hear. Then spam filtering, of course, you say, right? A lot of email clients you can train nowadays yourself and say, like, this is spam, this is not spam. And then recommender systems, Amazon, yeah, other customers have bought you might be interested in. So these are just some examples for supervised learning, of course. Unsupervised learning, you've already seen an example of unsupervised learning, what we did with the dimensionality reduction. That was a case for unsupervised learning. There was nobody saying this subspace would be good or look for this and this transformation in the data, right? We just said, here are data points, project them down. This is a case of unsupervised learning. Then there's the cocktail party problem. That's actually similar to the hearing aids. It's like you're in a room and there are different sources of noise. Like there's somebody talking, there's somebody singing, and I know somebody's having a discussion in the other corner. And you want to separate the sources and see whether you prefer to listening in on the gossip to your lower right or better on the nice discussion to your upper left, right? So this is signal separation, and this is called the cocktail party problem. And then fraud detection. Like you have a normal behavior, basically, of someone for a credit card, for example, and then suddenly something extraordinary happens. And you can solve this without having someone who actually said, this was an extraordinary event and this is one. You just take the data and you're basically looking for outliers, right? Fraud detection can be outlier detection. And then Google image search categories. I don't know if you've seen this. When you search for something, I actually thought this was quite cute. I search for sheep. It's just my daughter loves sheep at the moment. You can see you not only get the images, you get categories up here, right? I have clip art and very cute sheep and baby sheep. And I didn't tell it anything about this in the beginning. So what Google does is it takes all the images that answer your query and it groups them for you into different clusters. And this is also unsupervised learning, right? It found structure in the search query I entered. Then this is just for you, so you know that this is out there. I call this somewhere in between. Like I find it actually hard to categorize reinforcement learning into supervised or not supervised. Reinforcement learning is a classical example is a computer learning to play a game, right? Because if you play chess, there are a lot of moves until you know the end result. The end results, win or lose, is kind of a label that is given by you, but you don't really need a teacher because the computer has rules to determine whether it won or not, right? So in a way, it's unsupervised, but it's supervised because you get the information whether you win or lose. And then you need to contribute, you need to estimate the contribution of all the single moves, like how good were those moves and how much did that particular move contribute to the actual win or loss in the end. That is the challenge in reinforcement learning. And I actually found when I Googled this, that Chris Beaumont, this is just funny because he was the guy who designed all those cool problem sets from last year for the course. And he programmed a Flappy Bird agent. So you can see instead of sitting there and hitting that button for hours, right? He just trained an agent and that bird is now flying through all those tubes. It's gotten quite good. Actually, I didn't watch it for that long, but I think it basically goes through it. So I'm just saying this because I think it's a cool topic to be interested in if you're interested in machine learning. I don't see so much relevance for data science, so I just wanted you to know about this. And so this is kind of in between. If you hear about it, but we're not going to talk about it anymore. And then semi-supervised learning. Normally you have, this is good data science. You get a bunch of data from someone, and then you get a few labels. Let's say you have a music database, and you have access to all the tracks stored there. Like there actually are databases like this, which I think give you 30 seconds of all the songs out there, but you only have labels for a few. So you have, I don't know, 10 examples of classical music, but then you have the whole bunch of classical music tracks, but you don't know whether they're classical music or not, right? You only know 5 data points. These are classical music. This is rock. This is metal. This is house. I don't know. And then you cluster, basically, you do unsupervised learning mostly. You try to find patterns in that data. And you can use a bit of that labeled information to try, for example, infer labels for the patterns you found. So this is my all of machine learning in one picture figure. You will see this, I think, in every machine learning book out there. So the idea is here that you have a bunch of data points, red and blue. So this is a supervised problem, right? The label is the color here. I already know I have 2 classes of data points, and one is class red and one is class blue. And you can see the distribution of the points in this feature space. You see on the axis is feature 1 and feature 2. And then there's this line in the middle. This is called the separating hyperplane. What, sorry? I thought I did. Oh. It says stop pause. Oh, this I didn't do. Thank you. I'm sorry. Thanks for raising the hand. No video, no. Yeah. Now, yes. Good catch. Thanks. Where was I? Separating hyperplane. So all the fuss in machine learning is about finding that line. Something that can be so easy you can write whole PhDs about. Because there's, of course, a lot that this picture here simplifies and hides from you. But the supervised learning setting is you have those 2 classes, red and blue, and you want the line in the middle. Why do I want that line in the middle? Yes? Yes, exactly. Because supervised learning is about making predictions for future unseen data. And then if somebody comes with a new data point, I just look on which side of that line the new data point is, right? And if it's on the blue side, I say blue class. And if it's on the red side, I say red class. This is why this is so important. And it gets all more complicated when you have more than 2 features, right? Then your space gets very high dimensional. And then also this line doesn't have to be a line. And then it's about how much wiggle room do I give for that line. So this is all then where it gets complicated. But the idea is simple. And this is, even if you have very, very complicated algorithms, in the end, it's, at least for me, very helpful to break them down into this picture and try to think about what is happening in lower dimensions here. How does my classifier work? So here's a more concrete example that shows you that features matter. Just imagine you have a task, right? I give you a bunch of data points, and I tell you these are apples and oranges. And I put a lot of work and effort into it and measured how round they are and their weight. What are you going to tell me if I come to you with this data? Yes, you can't tell the difference. Of course, I cheated a bit here, right? This is simulated. Most probably oranges are a bit heavier than apples. I actually don't know. But these data points are generated from the same distribution. So if I ask you and say, but I want a classifier, what are you going to give me? Color? How are you going to determine the color of a new data point? It's really easy. Random. Yeah, you don't even have to bother about finding a line there. If I come to you like this, you just go, yeah, coin flip. Might be red or blue, I don't know, right? So the worst I can do is 0.5. Luckily, so what if this would be an unsupervised scenario? What would this look like? What was missing in unsupervised? It wouldn't be tagged, so yes, there wouldn't be colors, right? So those colors would be missing. All those points would have the same color. What would happen in an unsupervised setting? Like if somebody comes to you and just gives you that data, right? It's maybe a bit of a trick question. Yeah, exactly. They would be screwed all together, right? It's just one scramble. So you wouldn't even know that there are two classes in there. How could you? Right? So, and this is all because when I measured this and I put all the time and effort into like measuring the roundness and the weight of all of this, it doesn't give you information. I measured the wrong thing. I measured the wrong features. Those might be nice to describe oranges and apples, but they're not nice to distinguish the two classes from each other. So what you do is you send me back, right? You say, measure more, please. I can't do much with this. And I go back and think about color is actually a good indicator maybe, right? Oranges are orange, apples are green. So here you see now the color feature did the trick, right? This now separates the two classes. And as you can see, that separating hyperplane that I just manually put in there is orthogonal to the color. What does that mean for shape? Can you think about that? Yeah?
Shape doesn't help you tell.
Yes. Shape doesn't tell me anything here. That hyperplane is orthogonal to my feature. So if you think about when I determine whether the new point is to the right side or to the left of that hyperplane, all I do is I look at the color feature, right? So I might as well have not bothered with shape, maybe. So another really, really good example that machine learning is not as intelligent as we always think, right? I try to demystify in the beginning, because people often are like, yeah, great, machine learning, the computer can learn something. So when you guys drive a car, what input do you need? What? Visual, yes. You look outside the front window, and maybe also to the right, to the left, right? But all you really need are your ears. Your eyes. The ears can help, right? The ears can help, but most people out there are totally capable of driving a car just using visual input. Also in unseen territories, right? You can drive to a new city and find your way around. Even though you haven't seen that traffic light before, you know it's red, so I better stop here. So there's been these self-driving cars now coming up. This is an example of a self-driving car. I'm actually not sure whether this is the Google car or if it is the Google car, if it's the latest version. I used to have a Google car in my slides. And you can see here, this has way more than a video input, right? There is a camera up here, so this says video camera. Apologize for the small font. And then there's light detection ranging. So this looks how close other objects are. Then there's a GPS signal, a radar sensor, ultrasonic sensors. Okay, the computer we need somewhere. You have your brain too when you sit in a car. And there are radar sensors here as well. So this car collects all this additional information. In addition, at least the last Google car version I actually looked into, but that was, I think, 2 years ago, could only drive streets that it had seen before. It wouldn't have been necessarily the same car, right? You can have another car collect the data, and then you can drive along, but it couldn't just go to any city out there. So you need all these extra features. Don't go, like, especially I work in image processing, and I fall into this trap over and over again. I look at images and think like, yeah, this is easy, right? Sure, we can do this. We can find your membranes in your electron microscopy images. I'll come back next week. And then I come back next week and say like, huh, this was a bit harder than I thought. We need more. Yeah, so if you can, make your life easier by measuring the right things. Like if you can have influence on how you collect the data, right? What you scrape from the web. Think, when you design your final projects, think beforehand, what are the things that really separate my classes if you want to do predictions? Oh, we have this. This is just a new data point here. Actually, there are 2 ways to classify this new data point. One is just looking on which side of the separating hyperplane. Can somebody think of another way that doesn't use the green line at all? And this other way is what we're going to talk about in this lecture. Yes?
It's obviously a black dot, so a certain distance from the black dot.
It's a certain distance from a black dot. So this is only black here because I didn't know whether it was red or blue, right? It's a new data point. Nobody told me what it is. But you're right about the distance. So this is another way to look, right? You have your new data point here, and it's closer to all the blue points than to the red points. So this is another way to say this is a blue guy. So just naming conventions, because I think this is everywhere the same out there, like most probably in every machine learning book that you're going to take into your hands or statistics book. The data points are going to be X, and the labels are going to be Y. This is just standard out there. And so here I just get the data here and put it together. The plots before I simulated with X1 and X2. Now I put it into one variable and then create the labels for those, just concatenating them. So today we're going to talk about this classifier that just cares about how close is the new data point to other data points where I know the label about. And this is called KNearest Neighbors. So I predict the class of a new data point by taking the majority vote of points around it. And it's a very simple classifier, right? It's I think, the classifier out there that is easiest to understand, but it still has very good performance. So K here is what? What is K? If I say K nearest neighbors. What? How many clusters? No, that's K.
How many votes there are into what?
Yeah. Yes, how many points? Like when I have my new data point, I can just look at the one closest point, or I can look at the 3 closest points. And that's what K means here. And I know it's confusing because there are other algorithms, especially clustering algorithms there, right? K means where you also have a K, and the K is the number of clusters. This is not the case here. This K can be a 20, even if you only have 2 classes in your data set. So here's an example. We have a new data point, and we have our red data and our blue data here. This is from Wikipedia, but I really liked the illustration. So if you only say K is 3, right, then we're in this inner circle here. K is 3, you're looking at the 3 closest neighbors. 2 of them are red, 1 is blue. So the new data point here gets assigned a red label. If K is 5, I'm in this outer ring here. So these are the 5 closest data points. And now I have 3 blue points and only 2 red. So just by changing k, I just changed my prediction, right? So the choice of the k parameter here is important. So you need to think about it. The good news is it's basically the only thing you have to tune in most cases. Are there actually questions about this? Because this is, yeah?
Wouldn't that be affected by the number of blue and red points in the entire data set? So would you need
Yes.
to like, do some sort of transformation to correct that?
Yes. If you have a lot more training points, that helps. Yes, definitely. It's about the number of training points, and it's also about the shape of your decision boundary. Like how those data points look. This is maybe what you meant by transformation, like how those data points are distributed in the feature space, right? If it has like a very sharp point, for example, with the red guys, and you have all the blue guys around it, it's going to be hard to have more red points closer than blue points. Yeah? What's that?
I guess I was saying, what if like 90% of the points are blue and 10% are red? Then
Oh yeah, then you're again in trouble. This is a case where what we call unbalanced, right? So we're not talking about unbalanced classes today, but that's actually a very interesting problem for all of the classifiers out there also. If you have, for your project, if you have unbalanced classes, you need to deal with those. Like there are very few cases where you just get lucky and can tell the classifier only have 10 of the red guys, but 10,000 of the blue guys, and it still does a good job. So that's right. That's another thing to care about. I'm going to talk about that most probably when we talk about random forests. So this is how you can train a KNearest neighbor classifier. I'm using this scikit-learn library. This is a Python library for machine learning, which you're also going to use in the homeworks. Let's see. I really, really encourage you. I know you already went through all this Python learning, and then there was pandas, and now I'm coming with yet another library. But you're going to get incredibly fast coding if you know more about this. You're going to have examples in this lecture where I spent like 8, 9 lines of code. And in the homework, you're going to need 1, right? Because there are functions for nearly everything in there. It actually made, the first time I tried to design a machine learning homework, I had a really hard time because everything was already solved in there. So look at those functions. If you need something, most probably it's in there. So, and training a classifier, here's just a matter of saying, I want the nearest neighbor classifier, and I give it as a parameter the number of neighbors that it should look at. And then here, I just call the fit function of this classifier and give it the data points, x and y. Let me do that. So it's just a matter of finding the right classifier here, and then all the classifiers in this library just have this fit function here that you can call directly on the object. And I put the train here in quotation marks. Why would I not really call this training a classifier? Sorry? Yeah, I use all the points again, right? So the answer is, like normally when we say we train a classifier, what we do is we look for that separating hyperplane, for example. And then once you have the parameters of that hyperplane, you don't have to look at all the other data points anymore when you do predictions. KNN is what you can call a lazy classifier, because that fit function there in principle doesn't do anything, right? It just says here's the data that you need for predictions. As long as there is no new data point incoming, I don't need to do anything. So I'm pretty sure this guy actually does something, because it sorts the data in a specific way that makes it faster to compute distances and to get the k-nearest neighbors for future predictions. So it might take some computation time there, but it's not really what we would call training a classifier. So now we're going to predict labels here. So I have a new point that is in the coordinates 6, 9, 6, 9, somewhere around here, I guess, and 2, 4 would be somewhere around here, there. And all I have to do is I call the predict function of this classifier that I defined before and say, give me the prediction for those 2 data points, and I just put them in a list here. And you can see here it says 1 for one and 0 for the other. So the labels, it outputs here, the numbers are the labels. Yeah, wrong error. So which labels it uses depends on this Y here. This is one of the things where you put the data in, right? It looks at what labels are there in Y. Could have been 5 and 4. The algorithm there doesn't care. So just so you know, because some classifiers asked for your data to have labels -1 and 1 or 0 and 1, KNearest Neighbor doesn't care. Could have been 4 and 5. It's just because I defined Y to have the labels 0 and 1 for the 2 classes. So, and it's that easy. I get my predictions from my new data points. So now we want to visualize that decision boundary. So as I said, we want to look for that separating hyperplane. This doesn't really compute this hyperplane. Still, there are boundaries, right? There are areas around points where everything would be classified as class red or everything would be classified as class blue. We want to look at this. So I define a function here to visualize that decision boundary. And I say, give me the classifier. And these are just the coordinates, basically, of the feature space of the part that I want to visualize. And then there's a step size here and a color map. And I have a bit of illustration in the next cell. I'm going over this because if you look at the sklearn library examples, this comes up quite a couple of times, so I thought it would be nice for you to understand it. So there's this mesh grid function of NumPy. And to really understand what this code is doing, we need to look at this mesh grid function. And this is what it's doing. So here I have an array from 0 to 10 with a step size of 2, right? So this is 0, 2, 4, 6. And this is as well. So I have 2 arrays here. And then I use this mesh grid function, and this gives me 2 vectors, x, x, and y, y. You can see if I make a scatter plot of these 2 vectors, I get these grid points. Right? But all that I put in was a vector from 0 to 10 here, or actually 0 to 8. Right? 0 to 8. And this mesh grid function automatically generates the combinations for the points in the middle here. That's very handy to have. Also sometimes for other things like parameter tuning with grid searches or something. So that mesh grid function can be very useful. So if I just make a scatter plot of these points, I only get these blue guys here. And then in addition, there's this color mesh function. And you can see here it gets the coordinates of the points and then it fills them with a color. So this is where these patches here come from. Right? So my mesh grid here gives me the points, and then the color mesh fills the area between the corner points with the color. And this is exactly how this function here works. I have my mesh grid over the range of the feature space that I want to visualize, right? Where I want to get the decision boundary. And the step size here is small because otherwise it would look blocky. But it takes more computation time. So first important hint, if you have a slow computer, make this larger, right? Because then your patches get larger and need to do less classifications. And then here, I call this classifier and I predict the label for all these different grid points. So instead of, in the other example, I assigned random colors, instead of that, I now compute the labels for this, and I'm going to color the patches accordingly. And then you just reshape those colors, and then each of these patches gets the color it is assigned to. And this is what it looks like. Actually, did I need to run this? Let's see. No, I needed to run this. So here we go. We have our blue class, we have our red class, and now you can see this decision boundary. Now this is not really a line, right? Before I only had the separating hyperplane, there was a linear classifier. You can see the K-nearest neighbor decision boundary, right, is not necessarily a line. This is actually something that makes this classifier very powerful, that it can wiggle around the shape of the data points that you have. So enough with simulated stuff. Let's go to real data. I talked about this MNIST before. And MNIST is quite a popular data set. It's handwritten digits. And it originated somewhere in the 80s. All the deep learning guys did this. And I think the initial task was for checks here. When you have handwritten checks, and you give it to the bank, and they don't want to have someone typing in all those numbers. So already quite early, I think at least in the 90s, those checks were read automatically by a neural network, at least partly in the US. And people were very proud of that. You all don't look impressed, but that was a huge accomplishment to have a machine learning algorithm actually push that boundary that was that useful. So we're just going to fetch the MNIST data set. These are functions also within sklearn that just allow you to fetch common machine learning data sets that people use a lot to evaluate algorithms. And you get it in a dictionary. This is why this data.keys, if you want to look at this. So what you get back is this data structure. And what you care about is the data itself here. And then the target is the labels. So this is your X, and this is your Y. And you can see here I assign that. And we have 1,400 data points, and each data point has 784 dimensions. And I couldn't do that in my head, but 784 happens to be the square of 28. So these are actually image patches that are 28 by 28 pixels that we just loaded. So here we can, it's just an output. Whenever you get data, it's good to have a look at it first, right? In this case, we already know this data are images. So let's look at this, and you can see these are handwritten digits. They can be quite messy. Like, I actually don't know what that is. Maybe it's a 2? 2. So what I did here is I just permuted the data because it's sorted. That's also something to look for. When you load this data, it's sorted. It's only the zeros, then the ones, then the twos. Right? If we're going to talk about splits later on, you want to make sure that you make a random permutation, because otherwise, if you split your data into two halves, one is going to have one half of the labels, and the other one is going to have the other half of the labels. You don't want that. So here, this is how I did, how I scrambled them up. So I just called a random permutation on my X. Right? And this only permutes the first axis. Right? So all my samples still stay. This data point still has all the features it belong to. They just get sorted into random rows. So here's a scatter plot of that data. How we learned it before, right? So the SVD projection just got a lot simpler as well. Here's just a function in sklearn that happens to be called truncated SVD, and you just give it the number of components that you want. This is the number of dimensions you want your new data, not new, your data to live in from now on. So it's two-dimensional to give us a scatter plot. And then this is kind of a classifier, so it has this fit function. And because people use it so often to just transform those points into lower dimensional space, for your convenience, it's a fit transform function. So this does both steps in one, right? It fits that SVD, and then it transforms X to live in the two-dimensional space. And then we can just make a scatter plot. And what do we see here? So this is my data. It's good to have a look at this and just think about what you can already learn from the data by just looking at such a scatter plot. What I found really curious when looking at this for the first time is this up here. Without cheating and actually uncommenting the color bar and just looking it up, can somebody guess which class that is and why? What is curious about this class up here? They're all very similar. It's very dense, right? It's very compact up there. What? Yes, that's the one. Why is that one? There are only so many ways you can screw up a straight line, right? Like with twos, like I was hardly able to identify that other two. But it was just a vertical line. How many variations can be there, right? And it's indeed true that is label 1 up there. Here it's this blue shade. So for our SVD, I didn't verify this, but so these features here don't really have a name, right? Because there's not necessarily interpretability of those two dimensions we projected down to. Often there is, though. So it might be a bit that going down here on the y-axis is how wide, right? This becomes because the 0 is down here. I have the very straight lines kind of on top, right, with the high y value. And then the zeros, which are kind of wide, right, character-wise, are further down. So this can give me just an intuition of what this feature space might look like of the projected data. Can you all see that? Yeah? Okay. So now just look at just two classes. This is now 8 compared to 0. And I was actually surprised how good that separates. I thought those two would be more messed up, right? Because the 0 is kind of a roundish thing, and the 8, but maybe 8 just tend to be a bit more narrow. Don't know. So here you can see I just built a sub-index here with an OR. Either y is 8 or y is 0. And then I take that subset here of y just out by indexing with this Boolean array. And then this is a scatter plot of the two classes. So let's look further at these two classes and KNearest Neighbor classification and the effect of K. So if I just take these two classes and now put them into a nearest neighbor classifier and fit that just in those two dimensions, right? So I'm actually trying to see what is happening here. I don't care about the higher dimensions yet. And then I use my visualization of the decision boundary here and look at the results, and I plot the points in here as well to get an idea. So this is the result I get. Can I actually zoom this in? Yeah, kind of. Because this is still too small. So K in this case was 1. So it's only looking at the closest nearest neighbor, right? And this is classifying all the patches here. And you can see this is our decision boundary. Where is this decision boundary with respect to those 2 points? In the middle, right? So for K1, if K equals 1, you can kind of traverse your way here through the middle of those data points, right? This makes my decision boundary quite wiggly here. There's no straight line here. There are even islands, right? Where new data points that just end up in this island here would be classified as, I forgot which is which. Eighths? Eighths, I think. So a new data point just ending up here would be an 8. And my decision boundary here is so wiggly. What does that mean as well? If somebody comes and gives me a new data point and says, oh, by the way, I've just written a couple of more 8s. Here you are. What could happen to my decision boundary? It can change. Yeah, I heard the word. So just one new data point for k equals 1 can change your whole decision boundary. What? No, that's not what I wanted. Go there. What if we make k larger? Now k is 20. That looks a lot more like line, doesn't it? Yes? This is now in 2D all, yes. Yes.
What would you decide to compact it and then apply the algorithm versus apply it in a higher dimension with more information?
This is a really cool question. This is such a cool question that it's part of the homeworks. So yes, this is something to think about. What happens if you use more dimensions here and have the k-nearest neighbor classifier access to all those other dimensions? You're actually going to do that in the homework. You're going to test this and project it to different dimensions and then see how that changes the classification. Oh, all the way in the back. Yeah, loud, please.
Sorry, I had a follow-up on that. You talked about the dimensions of the SVD.
Yes?
Do those necessarily actually mean anything, or are they just like composites of the dimensions that you're like compressing down? Does that make sense? Like, are you losing information to make those dimensions smaller, or do those dimensions like?
Yeah, so the term information is a bit ambiguous here. I don't know if you remember when I showed you those 2D points projected into 1D in lecture 2 or something. If you look in those slides at the very end, I showed that if you project the points down to 1D and then reconstruct them, you end up with this line rotated into your former space. So you lose information in the sense that when you use the truncated version, right, you throw away information. And then you can't reconstruct all the points. If you're lucky, you're just losing noise, right? So you don't know. The other part of information that you lose is it's not really clear that those 2 dimensions that I project down to are going to have a meaning, like interpretability. There often is. Like I've seen nice, for example, of only 3s. If you only take the 3s and project them down, you can see that like if you point the data points that it gets from the thinner versions to the thicker versions, right? Even with like line strength. So if you plot those points, you can sometimes see information, but there's nothing in there that says there has to be. Like you're not influencing this. So, and what you see here now with this k is 20 now, right? So what happened to my decision boundary? Compared to before? Oh, I'm surprised. Yeah?
Sorry if you said this already. I'm not sure I understand the dimensions from which you are reducing. So what's your input?
Oh, very good point. Yes, very good point. Let's go back here. What are we looking at? This here. You're asking in the high dimensional feature space, what are my features? So this is a good point. Sorry, I just skipped over this because it's my daily bread and butter. So it was so intuitive. So this is an image patch here. This is one data point that you have. And each pixel of this image patch is 1 dimension. So these values range from 0 to 255. 0 should be dark and 255 should be white. And then you basically go like step by step by step, and like the upper left corner is your first dimension, next dimension, and so you end up with this 728 dimensions. This is your 28 by 28 image patch, and each pixel contributes to one dimension in here. And if you, it's actually also something if you just want to play around and have a look. If you look at those 2D data points and project them back, right? If you take these data points, project them to 2 dimensions, and then try to restore the original image patch in its 728 dimensions, what you're going to see is, depending on how many components you preserved when projecting down, you're going to have a very smooth version, hopefully, of this image patch. And because you're keeping the more important components of that S matrix. Like, okay, I'm going too deep into the math. I see puzzle faces. Sorry, I also don't have slides on this. Because this is also used for image compressing. This is where I wanted to go here now. Like, you can project those down, only have those 2 dimensions. If you reconstruct the patches, you're going to see that you basically still can identify kind of the numbers in those patches. So if that is all the information you care about, you don't actually need to store all those 28 by 28 bits. You only need to store these 2-dimensional data points and the information for the reconstruction. Yes, but very good question, thanks. So this is my high-dimensional feature space, 1 pixel for each dimension. So we're back to K and our decision boundary. What happened to my decision boundary here? What happened to all those islands? They're gone, right? Remember when K was 1? So this looks actually kind of like a line now. But what that also means is those islands had a reason, right? This guy here is brown. Like, this is an 8 in a swamp of zeros. If I now classify my training data, what's going to happen? If I just go back and ask the classifier, what is this? What's it going to say? Zero, yes. So it's going to make mistakes, even on the data it has just seen, because K is so large. So the value of K has a smoothing effect, right? It smoothes the decision boundary, and it comes at a cost, kind of. Maybe this is even what you wanted. So let me just get that back, because I need it later, right? So with K1, much more wiggly. But also we said, right, a new data point can change my whole decision boundary. This does not happen with K equals 20, or it's very unlikely to happen. So general observations, if K equals 1, this actually is so popular that it has its own name. It's called only nearest neighbor classification. So we're only looking at the closest data point. I get this very wiggly decision boundary, which can be changed by just 1 data point. And I think we're going to talk about this later, but there's something called variance and bias trade-off for classifiers. If K is small, you have a high variance in that decision boundary, right? I just want you to have first glimpse at this concept. So it wiggles around a lot, and you can think if I have different random subsamples of my data, this decision boundary is going to change quite a bit, right? Even if those data were generated by the same source. So I have a high variance, but I have a low bias. If I would average over a lot of these decision boundaries, I had to have a good chance of ending up with a nice decision boundaries along the actual distributions of the data points, even if it is irregular in shape. If I make K very large, I end up with a very smooth boundary. I have a training error, right? So if I predict my training data points again, I actually make mistakes on the data I've seen before, but I have a low variance. So even if you do this random subsampling, because K is so large and your boundary is smooth, you're most probably going to end up with nearly the same thing. So the variance is then low, but you have a high bias. If your actual decision boundary is very wiggly, you'll have problems seeing that, like getting that decision boundary. So I actually wanted to take just a short break here. This is cool because you guys actually have all paid really cool attention. I would like to give you 5 minutes and discuss with your neighbor what you think are the strengths and weaknesses of KNN. maybe you don't need 5 minutes. I basically want you to think about what is the scenario where you would use it and what would be an absolute no-go. Just think about this. Which final project ideas are in your mind where you would say, yes, this is a great idea? You go like, no, this would not work. Like, don't be shy. I think everybody in this class is really nice. So I think maybe people have some results. Is this on? Is this on? Yes, it's on. Let me hear your thoughts or discussions, results. What are scenarios where we would say, this is, maybe start with the easier part, I think. Where is this a no-go? Where would you say, like, yes?
Maybe the scale of your features are really different. You might have one that
Yes.
uses like discrete values, like nominal attributes, and the other one has a scale of like 4,000.
Yes, very good point. Yes. If you have data points that are represented by features, I mean, this was every pixel in there, right? Has a nice range from 0 to 255. It's like all kind of in the same scale. If your features are all over the place, right? And you have one ranging from, I don't know, 0 to 1,000,000, the other one from 0.5 to 0.8, and you just dump it in there, then this is going to run into problems. Yeah.
Would you be able to like solve that by normalizing?
Yes, this is something you can take countermeasures. Yes, for that. exactly. So other ideas where you would not go with KNearest Neighbors? Yes? If you have a small data set, yeah? Small data set with lots of features, yes, you would run into trouble. This is called the curse of dimensionality. If you can imagine, maybe if you have a box, right, and you just have the lid of the box, and you have a couple of bolts, and you fill the whole surface of the lid with those bolts, nice and dense. And now I take the same number of bolts and just put them in the box. I still have a lot of space inside the box, right? So you can imagine that you need a larger number of data points to fill a high dimensional space than you need for a low dimensional space. So if you have only a few data points in very high dimensions, this can also run into problems. There's a very, very practical reason not to use it in certain applications.
Very expensive.
Yes, we're going to say that as well. It's like super computationally heavy, right? The training is so lazy and easy. But afterwards, when you want to do your predictions, it has to go over the distances to all of your training points. So if your data set is really, really large, that is a lot of computation. And you have to repeat it for every single prediction you have to do. So if you want a lot of predictions, you need them fast from a big training set. You need to think about this because KNearest Neighbors is useful. There are certain tactics that try to make it faster, but it's a severe limitation. Yeah?
Imagine a scenario where you know more about either the underlying distribution of the data or how it was generated, that you can't just assume that because two things are close, that they're not close to maybe some other metric that would be a better judge.
Yes. Yes. So we've only used the out-of-the-box KNearest Neighbors, and it's quite easy to use, right? But if you know more about your data points, about the space they live in, the examples I've showed so far were all just Euclidean distance, right? The distance between the points. So you might want to think more about how can I put maybe prior knowledge that I have into knowing the distance between points, right? So these are other things you could think about, yes. So what is it really, really good for? I started with the negative point, so nobody's going to like it anymore. It's still out there. People invest a lot of time, right? Making GPU implementations, in like computing tree structures to make the search really fast, coming up with distance measures. Why? What is it good for?
It seems like it worked pretty well.
Yes, it works great. Yes?
We have a lot of data, not a ton of dimensions, and those dimensions are essentially orthogonal and very distinct.
Yes.
Of each other.
Yes, that's a good scenario for any machine learning algorithm nearly out there. This is exactly what you want to have, yeah. But you've already also pointed out it wants the data to be fairly nicely behaved, right, with this. But the other really, really cool thing is you understood this guy in 10 minutes, right? And you can have an idea of what is actually going on. And there's only one parameter, except for if you go into more complicated distance measures. It's only k. That's all you have to worry about. You haven't seen the more complicated ones. But if you have a support vector machine, you need to decide for the kernel. Then you need to decide for the parameters of the kernel. There comes a lot more baggage with these other classifiers. This is nearly off the shelf. Like, as long as you live with the simple distance metrics, k is the only parameter you need to worry about. So these are very, very good reasons to use it. So, but we do need to worry about k, right? So how can we choose k? We don't want to just choose any k out there, right? We've seen that if it's only one, then the decision boundary is quite wiggly and can change a lot. If I make it too large, that decision boundary can get too smooth, and I make maybe mistakes. Sorry. So what do I care about when choosing K? What I care about is the prediction performance, right? When a new data point comes in, I want to make a good prediction on that new data point. This is called what we call generalization. The classifier should generalize to new unseen data. And in order to tune K to give me that good generalization performance, I need to measure the performance of K and then choose one. And for that, I need to bother a bit with error measures. So we had a two-class problem here in the end. We had a class 8 or class 0, depending on what digit it was. And then there are general, for binary classifications, there are these 4 cases that can happen. You can have a true positive prediction. This is, so normally you can think also, it's maybe easier with foreground and background, right? If one class is the foreground of the image and another class is the background, it's easier to associate positive and negative. Or if I say, is this a face or not, right? It's binary classification, it's the same case, but it's maybe easier to understand about the positive and negative. So is this a face, yes or no? And if it is a face, and the classifier says, yes, that's a true positive, right? Then I have a true negative. It's not a face, and the classifier also said it's not a face. Actually, I think I have an illustration. Yeah, I stole this. So you have the classifier, what it says about the data, and you have the actual label. You know that because it's a supervised setting and somebody told you what it is. So the classifier says, yes, it's a face, and it was a face. That's a true positive. The classifier says it's not a face, and it is not a face. Then it's a true negative. So this is what is called a confusion matrix. And what you can see is in a confusion matrix is you have those correct classifications in the diagonal. And then to the offsides, for the binary case, you have the 2 remaining combinations that there are. So the classifier says, yes, it's a face, and it actually isn't. Right? It was just a funny looking picture. And the classifier says, no, this is no way that this is a face, but it was. So these are the 4 cases that can happen for binary classification. Now we have actually more classes if we take the whole 10-digit problem, right? So I would have here all the different classes, and it's not about yes or no anymore. Do I actually have that? I think I have that later, sorry. Let's take the binary stuff for now because we have 0s and 8s. So what I do here is I set K just 20, I train my classifier, do the predictions here, and then have my confusion matrix. And you can see my diagonal looks pretty decent. It's not 0. Like these are the true things where I didn't do any mistakes, right? And these are my mistakes. So 18 points were wrongly classified in this case. And you can see here, again, the library gives you a nice function that already does all the work for you. Here's a function called confusion matrix, and you just give it the predictions the classifier made and the true labels, and it's computing everything for you. No need to bother around with NumPy arrays, filling them yourself. So this is what a confusion matrix can look like if you just look at it in that color representation or gray value representation. You can see this is what we want here. We have high values in the diagonal. These are the points that were classified correctly. And then on the offside, we have nice low values. Now it gets a bit more complicated. So now I, again, leave K at 20. And now I do the predictions for all the classes out there and actually do them in the high dimensional space. And this is the confusion matrix you get. Can you see that? Oh, it's very, very faint. But it's like, can you see that there's a brighter stripe here? Like under the 1? This is something that confusion matrices are very useful for. Like it can show you, actually what does this mean? What does this mean? This is the predicted label, and this is the true label. What does our classifier like to do? Yes? Yes. The classifier is very eager to find ones in the data set, and it's a bit too eager here. And this is what you can see. These are insights you can get by plotting the confusion matrix. This is why we look at it. So this is also where the name comes from, right? It's confusing a lot of the other classes with one. Yeah? Yeah, this is actually a good question. The question is there a summary statistics? I went for accuracy. Here, this is what a lot of people do. There are drawbacks to that choice, maybe, but it's like for multi-class, it's still an open question what are good metrics, but this is one that works. So you can summarize the performance of a classifier just as its accuracy, and this is the number of true predictions divided by the whole number of data points that you have. And again, scikit-learn has a nice function that does that for you. And normalize here makes sure this is between 0 and 1. If we go to 0.88, that's decent. So evaluating the choice of k, I have a function here that now computes the accuracy for a given k. So I have my KNearest Neighbor classifier, and here you can see I have the parameter k up here, and I give it here to that classifier, and then I fit the data that this function was given, do the prediction, and then return the accuracy score. So this is a simple function that just gives me an accuracy score for a given k, x, and y. And now I can use that function to evaluate different choices for k. So I can plot this. These are the different values for k, and this is the accuracy. Now k is discrete, so maybe the line plot is a poor choice here. Should have paid more attention to the visualization lectures, maybe. So, but also the code that I wrote here is very inefficient. Can you see why? I have this. So what I do is I initialize an empty list, and then I go over different values for k. I just say k is between 1 and 50. And then for each of these possible values, I actually compute the accuracy of the classifier. And I append the new value into that list. Why is that code inefficient? Is that a word? Yeah?
You should not grow the rate.
Yes. Yes, you should not grow the list. It's this is inefficient because in each iteration here, it changes the size of those accuracy value lists. It's appending an item, an item, an item. Now for this were just 50 elements, right? So it doesn't matter much. But if you do this a lot, this can get quite slow because you need to rearrange all the memory internally. So it's better. What should you do instead? Do you know? Yeah?
You should specify the size.
Yeah. Pre-initialization is what is more efficient. I could have done, I already know that k here has like these 50, oh no, 25? Only did steps of 2 here. But I know how many values of k I'm trying. So I know how many values I actually want to store. So I could have initialized this to its right size and just filled it up, right? And that can be more efficient if you have a lot of these loops where you want to collect data. So something else we're seeing here. The accuracy is really cool for a small k, and then it drops. Why? It's a more advanced question, maybe. What happened? This is k equals 1 with the really good accuracy, yeah? Yes. I'm doing a very evil thing here. I'm computing the accuracy score accuracy score for my training set. This is what you've seen before, right? When we had k was 1, you remember this wiggly decision boundary had these islands because it wanted to classify every point of the training data set correctly, no mistakes. This is why I get this really, really cool accuracy here for k equals 1. And then when I increase k, the accuracy drops because now I'm actually misclassifying points from my original data set. So this is the reason here. Now let's do this properly. We actually want a validation set, is what it's called. So I train my classifier on one set, and then I have a second subset of my data, where I validate the performance. So now we do the same with validation. It's nearly the same function. It now gets a random state here. And now I split the data. Again, scikit-learn comes with a nice function for this. I split the data, and I did this in 2 lines here because it got too long for the slides. You can do this in 1 line. So now I have a train set and a validation set, and a train and a validation set of my labels. And you can see here the test size is 0.33. This means that 1/3 of my data ended up in the validation set. And then now I again have my KNearest Neighbor classifier. Now I fit it on the training data, but I do the prediction on the validation data that is junged, right? So I train on my training data, and then I predict for new unseen samples, right? This is what it looks like to the classifier. I didn't know those data points were there before. So I'm simulating the situation where somebody comes to me and gives me a new unseen data point that I don't know the label for. In this case, I know the label, of course, and I need it to compute the accuracy. But this is what we're aiming at. So now we do the same with the validation set. Once a bit. And here's the output. Quite a different story here. So this was before. This is my training accuracy. And now this is my validation accuracy. And what you see here is for k equals 1, it's actually the total opposite, right? It's the worst performance. So if you would have evaluated on your training set, you would have chosen the worst parameter setting possible for your k. And that's an important take-home message. Also, never, ever report the performance of your classifier on your training set. It's always too positive. This you see here, right? Yeah, my classifier works great. Classifier it always has an accuracy of 0.94 and even 1 sometimes. Yeah? But it's totally meaningless because all classifiers should do well on the points they've seen, right? Worst cases, I just learn them by heart. What I really care about is the predictions on new data sets, and I'm emphasizing this because they're even now still very rarely, luckily, but there are papers published where people compute their scores on their training set and go like, yes, I did it, and no, you didn't. So in the final projects, please, everybody, you can compute a training score and report it because this is called overfitting. Yeah, this is what is overfitting with k equals 1. My decision boundary is so wiggly. I had these islands in there, right? Because I made such an effort to classify everything. I gave so much degree of freedoms to my classifier that it really could do everything right on the training set. But it ended up having these islands of points that were just there by a very small chance, right? And if I would have had a ton of more points, there would have been so many brown points around that blue island that it actually wouldn't exist most probably. So the classifier kind of captured noise in the data, and this is what we're seeing here. So the important take-home message, I'm nearly out of time, is use validation tests and use sets and use test sets. And I'm actually going to close now because this is so important to me, and I'm going to ask Raphael to give me a bit of Thursday in the beginning because I really, really want, or maybe he's just going to talk about cross-validation. But this is a concept that is really important.